We'll make this quick video to make sure that we all know how to use exponential regression on the calculator. So exponential regression on the calculator is just like all the other regressions that we've learned: linear regression, quadratic regression, cubic and quartic regression, just like all those things. Now, the function on the calculator that you will see is y equals a times b to the x. So the calculator is actually making some assumptions about the graph, and it's important that we discuss them real briefly just to make sure that we don't make any mistakes. So A represents the initial condition, and then B is our our growth constant, basically. So remember, if R is a growth, so R is positive, then B is going to be greater than 1. And if R is a decay, that means B is going to be less than 1. So if our rate is growth, our growth rate will be bigger than 1, and R being a decay means that this B would be less than 1. Then we have this to the x power. So uh, our graph will look something like this if it's growth, or it will look something like this if it's decay. But those are basically the only two things that I can have. There's really no other way of going about this. And so, therefore, um, I need to make sure that I'm fully aware that the asymptote is always 0, because we don't have in this equation any vertical shift. So, because the calculator is not assuming any vertical shift, we have to keep this in mind. But there is a shift that's okay. So, horizontal shifts are okay. And that's because the context is just a change in time, usually in the problem. So that means after I started counting 5 minutes later, it would be such and such. Well, what if you started counting earlier? That would be okay. So horizontal shifts are okay. The things that are not okay are vertical shifts. Vertical shifts are not okay in these types of problems because we have to assume that we have an asymptote at 0, because there's no other way to go about it in these problems. They don't have a plus C or anything. So let's do a couple of quick examples. Given 218 and 354 are on an exponential function. So stat edit 218 and 354 are going to be on the function. 218 and 354 are on the function. Then I go to stat, calc, just like we always have. And we have linear regression, quadratic regression, cubic regression, all those things. We're going to go to exponential regression, which is option 0. So exponential regression is option 0. We can store the equation, remember? So vars, y vars, store it as y1 if we want, and then calculate, and we'll end up with this function. So y equals 2 times 3 to the x. So y equals 2 times 3 to the x in this problem. And if you plug in 2 for x, you'll get 18. You plug in 3 for x, you'll get 54. It works out great. Now, what if I made a horizontal shift? So notice that what I did for this is I just did a horizontal shift to the right 2. So it's now 418 and 554. Well, if I go to exponential regression, remember it's option 0, and I calculate, I'm going to end up with a different A value, but the B value is the same. Remember what the A represents. The A actually just represents the initial condition. So y equals 0.2 repeating, so that's 2/9 times 3 to the x. So we're actually okay here because this 3 is our growth rate, or how much it's multiplying by essentially every time there's an x change. But the A is just the constant. So, like the initial amount. So, the initial amount is the only thing that's different. And it doesn't really matter if the initial amount's different. That's okay. So, if we have a horizontal shift, we're fine. A vertical shift, not so good. One word problem: there's a bacteria growing in a science experiment, and it looks to be exponential. When a student took count of the bacteria after 5 minutes, there were 150 cells in the petri dish. So 5, 150, and then 15 minutes, 350. So let's find an equation for this. So if we go to stat, edit, 5 and 15 are the minutes, 150 and 350 are the cells that are associated with those minutes. So now we're going to go to exponential regression, and I will store this. I keep hitting second, but I don't want to. I will store this in my y equals, as I may need it to answer the next part of the problem. I get 98.19805.061 times 1.08842292x. Now, one thing that's kind of important is that we don't want to round right now, because we're doing an exponential growth problem. So if we round early, that's going to cause us a lot of problems. So we definitely don't want to round early. So we're going to keep as many decimals as our calculator has. So we're going to want to keep all of these decimals. We can round to 3 decimal places at the end of the problem, but at the beginning of the problem, we don't want to do that. How many minutes into the experiment will there be 1,700 cells in the dish? So we would type 1,700 in for y. So we have 98.19805.061 times 1.08842292 to the x. And we can solve this by dividing by the 98 thing and taking a log base 1.08. But if this is a calculator problem, which this is, I can just leave that as my y1, make 1,700 my y2, make sure that I have a window that's going to be appropriate. So I would assume that it would happen within the first 100 minutes of the experiment. It's probably going to happen well before that, actually. And then I need my y max to include 1,700. So let's go up to about 2,000. And then I can second calc, find the intersection, and then just hit enter a couple times, and it'll find the only intersection that there is, which is 33.653. So there's where I can round to 3 decimal places. 33.653 minutes into the experiment, there are 1,700 cells in the dish. So one more time, even though this is an initial amount of cells and this is a growth rate, we can't be rounding these numbers, because we're going to be off by a very considerable amount if we do, because we end up having with what's going on, we're multiplying by these numbers repeatedly, and so then we get off by a very large amount.